Hello everyone. Today we are continuing to create an example about the 2D GMM model, Gaussian mixture model. Okay, and so we're one or week 7, 2D GMM X. In the previous lesson we have talked about the 1D GMM formation. Okay, but now we must utilize some important library in the Python, which is known the CGPy. Okay, and we built our own Gaussian mixture model for the 2D dimensional data. Okay, and also we need to add the stats import multivariate normal. Okay, and so firstly, in order to classify the hard data set or the model based on the GMM models, okay, we need to generate the synthetic data. MP random seed 42 and data x1 is equals to the MP concatenate, and so we need to add this one, MP random normal location 5, scale is a standard deviation, and size is equals to 250. Okay, and also we need to copy all of these terms, and then 24, 3 and 75. Okay, same as with the first one, we need to create the second dataset in here, the location 15, 12 and 2 and 2. Okay, and then we need to create the data MP column stack should be called with the tuple value next to, and so to print data and print data shape. Okay, these are important because we need to analyze this data set in here just like this one, and so this creates to the to the 1000 and the 2 data, which means that we have the 2 column values and also we have the 1000 data in here. Okay, so we need to build to the to the PLT scatter diagram in here in order to visualize the R dataset. Data 0 and the whole row values 1, and alpha, the opacity rate, is assigned to the the 0.5. Okay, and after that the PLT title should be given in here, synthetic 2-dimensional data set. Okay, PLT X label X1 and Y label X2. Okay, PLT greet true and PLT show must be given. So we have 2 kind of data set, but we don't know right now which data set are in the class 1 or class 2, and so we need to utilize to the to Gaussian mixture model to model everything which is given in here. Okay, so in order to do that we need to build the expectation maximization algorithm. Okay, just like in the previous lesson, def initialize parameters. First of all, the num components must be given in here, and data dimension should be given in here, and pi should be initialized with the MP once num components divided by num components. Okay, and so the means should be calculated with what the np random rand values, which is in here, and num components and data dim, okay, times np max data, and axis should be assigned to the 0 raw values, okay. These are the random values. This is the initialization of the expectation maximization algorithm, because if we add the random values to the pi, mean, and covariance data, and so we can identify easily. This is called the persistency of execution, okay, in the control literature. Data dim should be given in here in a 1, and so for each component must be assigned with the what, with this one, okay. After that we return to the what, the pi, means, and covariance. So we need to define also the def Gaussian PDF, okay. X, mean, and covariance should be given in here, just like this one. And so we need to return to the what, the multivariate normal. This is the implementation of the Gaussian mixture model in a higher dimension form, which is defined in the CGPy, okay, scientific Python library. And so the mean is assigned to the what, to the mean, and so the curve is assigned to covariance, and the PDF X must be returned in here, okay. And so after that the expectation step should be given with the data, pi, means, and covariances, okay. And k is the R dataset dimension, and len pi is the component number k, okay. And so resp np zeros must be assigned with what, the n and k in here, okay, responsibilities. And so for k in range of k, resp k, which is equals to the pi k, this is the weighted probability distributions in here, Gaussian PDF data, and means k should be assigned in here, and also covariances k should be assigned in here. After that the rest must be assigned with the what, the division rate of the what, the summation of the whole terms. This is just like the softmax layer, guys, okay. Keep dims true. The whole probability, or the summation of the probability, must be going to the what, 1. But if we divide the whole the rest to the what, to the total value, and so we normalize the whole the probability rate in here. And after that we need to continue with the what, def maximization step. Data and resp should be assigned in here, and k must be assigned with the what, the same way, len data and resp shape of 1, okay. And so and k is equals to the resp sum axis is equals to the 0, and also the pi is equals to n k divided by n. And so the means is equals to the what, resp dot t at or times data divided by and k total elements with a none, okay. This is the array representation of the what, the one-dimensional data. We can use the none in here, okay. And so the curves can be assigned to empty list, and after that k in range of the k, so difference of the data minus means k, this is the residual values, and so the curve k is assigned with the what, with the diff times responsibility rate of the k to k plus 1, and so t at diff divided by nkk, okay. This add is the multiplication operator, okay, and so this t is a function, and so it's a dimensional operator. So cos k is given in here, and cos append is filled with the what of cos k, and so we need to return to the what, to the pi, means, and cos. Okay. So log likelihood should also be defined in here: data, pi, means, and covariance. Okay. So the k is equals to the len pi, and like MP array should be initialized with the what? With this term pi k times Gaussian PDF, data, means k, and covariances k. Okay, this is the log likelihood, but for in the what? For k in range k. So these are the calculation of the Gaussian PDF with a weighted rate, and so we need to return to the what? The MP sum, the total log likelihood energy can be returned with what? The MP log like sum axis 0. Okay. So these are the utilization function, and the main code is started in here. Okay. And so first of all, the num components can be given by with the tune. Okay. And so we need to define the maxiter. This is the what? The maximum count to what? To converge the whole, the mean, covariance, and the responsibility, or the pi values of the what? Our algorithm. And so this maxiter is used as a 10,000s, which means that at the 10,000 steps we converge the whole the data, or we can define the tolerance of the error 1e minus 7. Okay. And so the pi, means, and covariances can be assigned or the initialized with what? With the num components, and the data shape 1. Okay. After that, the prev log likelihood is assigned to the none. Okay, and so we need to compare the prev log likelihood and the current log likelihood in order to what? In order to calculate the residual error or the tolerance of the R algorithms. Okay, so for IT in a range of max iter. Okay, and so this is the E step, rest, expectation step, data, pi, means, and covariances. Okay. And after that we maximize the whole data, pi, means, and covariances. Okay. Maximization step with the what? Data and responsibility values, and so we need to check the convergence in here, just like this one: LL log likelihood, data, pi, means, and covariances. All the time we compare or we calculate the absolute subtractive values of the what? The data and this distribution in terms of the pi, means, and covariance. And so if prev LL is not none and absolute values of the what? The LL minus prev LL is smaller than tolerance, and so we need to break. Okay, this is done. And after that, at all the time prev LL should be replaced with what? The current LL. And so the print final P is to what? Pi, and final means is the means. Okay, and final covariances is assigned covariances. Okay, or we can use this syntax for C in covariances. There's more than one the array in here, print C. So if I run this code, and then this is our data set, and after that resp shape is not known in here. I'm sorry. So we should give maximization step, resp shape, and k. If shape 1 must be given in here, y, so it's okay. The maximization step, resp shape, we have an error in here, just like this one. Data resp and k, land data and resp shape. Okay, there's no problem here. Oh, okay, and so we need to go to the what? Maximization step. Calling in here, and in this case, the resp is read in here. P means variance. Okay, expectation step, the expectation step, and k lamp pi resp zeros. Yeah, this is also true. K in range k, pk Gaussian PDF means, and covariance. And I'm sorry guys, we need to return it in here. We don't do that in here. Okay, you forget resp. Okay, so this is the R data set. Okay, and after that, this is to what? To R covariance, means, and the pi value. Just see that the pi is converging to the what? The 0.75, the other one 0.24, which means that 250, 750. Okay, so after that, we need to visualize the whole data in here. Visualize the data, GMM on grid. So X range is equals to MP linspace data, the whole row values dot min, and data whole row values max, and 100 point should be assigned in here. So the Y range is assigned with what? 1 and 1. Okay, this is the demonstration. XX and YY can be obtained with the mesh grid operator. X range and Y range. Right now it's empty, and so the grid can be built with the LM-MP column stack in here, XX rival and YY rival. Okay, this is a specific function, rival, and so in this case GMM distribution must be built with what? The MP sum. And so we need to give the list in here, pi k times Gaussian PDF, and so we need to fit the grid as a real data in here, but we should give the means and covariances. Okay, just like this one, and for k in range of num components. Okay, these are the syntax. This is the comprehension syntax, and after that we need to give the axis is 0, and GMM distributions is assigned to GMM redistributions. Reshape should be called XS shape, because the dimension of this data is built between the XX and YY. Okay, so we need to build the contour in here, XX, YY, GMM distribution, the levels 10, and the colors red, and the opacity rate is equals to the 0.5. MPLT scatter should be given in here. This is the real data, and we can compare the contour with the scatter values. Scatter values is the real data, and 1 and alpha 0.5. And PLT title is equals to what? The GMM distribution on 2D data. PLT X label X1 and Y label X2 and PLT show. But firstly we need to build the grid. True. Okay, so if I run this code, this is our data set, but in this case we can build the contour just like this one. This is the unit circle for the what? For modeling of the what? The GMM components. One of the component which is given in here, the other one is given in here. Okay, so we can classify the whole data based on this information. We can learn using the expectation maximization algorithm from a data. This is the unsupervised learning, guys. Okay, so what happens if I choose the num components for? See, in the for, just see that we have one component in here, one component in here, 1 and 1. 1, 2, 3, 4. See, we have 4 components. We can have the 4 model in here. Just see that the final P 0.005, 24, 74, but we have 2 small components in here. What about the 8? See, and so in the 8 we cannot solve this problem because the input must be symmetric, positive, definite, which means that our Gaussian PDF or the GMM distribution cannot solve this problem. And so how can we overcome this problem? This is simple. We should use an advanced or the more stable algorithm. And so in order to do that, we need to continue with the what? The second example. XCGPy library. Okay? That's the second example. So firstly, we need to import numpy smp and import matplotlib.pyplot as plt, and from sklearn mixture import Gaussian mixture. Okay, this is the standard build or the built-in function to be used in the what? In the GMM classification, guys. Okay, first of all, as we know, the synthetic data must be created with the what? The MP random seed, for example 42 in here. And so the first signal, x1 signal, is equals to the what? The data x1 class 1. MP random normal distribution can be assigned with the what? The location, which is 5. It's the mean value. Scale is the standard deviation, and size is equals to the what? 250. Okay, and so x1 2 class is assigned with what? The 24, 3 and 7. Okay, and so data x1 is assigned with the MP concatenate, which is equals to the data x1 class, data x1 class 2. Okay, so with the same analogy we can build the what? Another x2 signal in here, just like this one, x2 and x2, x2, x2. Okay, and so the 5 2 scale. Okay, and so we can assign the 2 value, just like in the previous example. Okay, so data must be collected with the MP column stack, data x1 and data x2. And so we need to visualize the data set in here. PLT scatter, data 0 and data 1 and alpha is equals to 0.5. Okay, and so the PLT title should be assigned synthetic data set to the PLT X label X1 and the other one X2. Okay, and so PLT greet true and PLT show. If I run this code, and then we will have this dataset just like this one, but this must be assigned to the what? This is not the 5, 9, and this is the 17. For example, we can choose that. This is more close to the end, but in the first place, we need to assign 28 right now. In the second place, we will try to the closing points to be utilized in the GMM algorithms, okay? And so, how can fit and build GMM? So, the num components. This is the first case, 2, okay? And so, GMM Gaussian mixture can be called with the n components, the num components, and the random state 42, okay? And so GMM fit is a specific function for a given data, and so we can find the whole, the mean, responsibility, and the covariance values of the what of this data. And so the 4 component in range of num components, and so we can print to the what f component plus 1, okay? And so mean this is the what we should return GMM means value, the component, okay? And after that, just like this one, the covariance can be obtained with the what? With the covariance, okay? And also we need to give the print. So if I run this code, and then we will fit the whole the data just like this one. This is the mean value, covariance value for a component 2. This is the component 1. Component 1 has 28 just like this one, and 12, and other one is the 8 and 5. See that 28 and 8, right? This is 2 and 12 and 5. 12 and 5. Okay? See? We can model it just like this one. But in order to visualize the whole data set, and so we can copy all of these terms because it's the same with the previous one. Okay? Visualization. Okay. And so we don't need to do that right now. The GMM distribution can be built with the MPX and GMM score samples from the grid points, and so this grid point is utilized with this one, okay? X range 100 100 and column is assigned in here just like this one. Score samples, Jemison reshape XX and 2D data. So see, this is the what the standard built-in solution for the Gaussian mixture models, guys. Okay, but what about this one? If we choose the 6 components in here, so see, in the 6 components we have 3 distributions in here, 3 in here, the other 3 are given here. In the previous case, we can contain to the what the smallest point, and so our algorithm, it breaks when it to the what increasing the number of components in this signal. But the solution method or the convergent method in normal case for a Gaussian mixture are different right now. And so if we assign the 12 values, and so just see that we have more than 1 signals in here, and so this contour are different line segmentation right now, okay? Or if we assign the 24? See? So there is more than one regions in here. One region, class 1, class 2, class 3, class 4, class 5, class 6, class 7, class 8, class 5, and blah blah blah. All the components can be built with these terms. For example, 64 can be assigned in here. So the algorithms returns to the what? To this output. Okay? So this is the case, and so in the 8 we can say that we have this kind of distributions. Okay, and so we can assign the 16 in here, and so in the 16 it's very good. Okay, so what happened if I choose the 5 in here? See, this is not close. Okay, and so what happened if I choose the location 18 right now? See, this is close, and so in this close we can right now discriminate this class data in here. But what happened if I choose the 16? It's more close right now, and so these are two the different regions in here right now. Okay, and so if I increase the components of this one 32, and so we always have the right hyperplane in here to discriminate the whole data. But if I choose to 14 in here, so this is too close right now, and so in this case we have to the the undefined behavior, just like this one. At this point we don't know which class possessed these features. Okay, but if I choose the 13 in here, it's more than correct, and so just see that we have 2 dimensions in here, and so which we don't know which class possessed which data. Okay, the easiest way to detect the class representation in here, we can set it to 2. Okay, this is the simplest way, and so one of them is given in here, the other one is given in here, but maybe we cannot identify this process, and so we need to convert this data into the another dimensions, or another method should be utilized to classify or discriminate this data, which we can call it to the neural network. Okay, or convolutional neural network. And so what's the purpose of utilizing the neural network? Neural network does not create a single or the continuous contour. We can create the non-linear lines or the ellipsoid to classify our data, but in the GMM model we cannot do that. We always find the mean and covariance value with the with the responsibility or the pi values in here. Just see that in this case we have these values in here, just like this one, but we don't know the responsibility values of these terms, guys. Okay, so any question? So if there's no question, and so we will take a break at 10 minutes, and after that we will continue with the DC motor example to find the regime for the current or voltage or some other parameters under the nonlinear conditions, guys. Okay.